welcome to Linear Algebra Day 2. Last time we discussed sort of at a high level what we're going to do with linear algebra ideas in the context of data. And we started in with some of the most basic linear algebra ideas. Try to paint some geometric pictures that you can carry around with you as the way that you think of those things principally. So just to review that a little bit, we talked about flat geometric shapes like lines and planes and higher dimensional generalizations of those things. And we talked about why it's useful to think of them in terms of vectors. So the idea was we'll take vectors that sort of run along these shapes, like a vector that runs along a line or two vectors that sit in a plane, and we'll describe the geometric object as the set of all linear combinations of those vectors that we grabbed that lie in the line or the plane or the higher dimensional generalization. Okay, and this was sort of our picture that we used to start thinking about span and linear independence, which are two of the most fundamental ideas in linear algebra. This word linear here should be bolded. That's a typo. It's a two-word phrase. So let's talk about span first. If we are going to talk about the span of a thing, what kind of a thing does it have to be? So this is sort of a computer science-y kind of question because it's about types. It's asking us to make sure that we know what kind of thing we can do stuff to. It illustrates a point that I think is often underestimated in mathematics education, which is that types are really important. If you're performing operations with things, it really matters that you know what kind of things that they are, because they support different operations. They might support an operation of the same name that actually behaves differently. And it's really hard to get things straight in your head if you don't know what types things are. And this point is often brought up in the programming context, because there's sort of a conflict between languages where things are explicitly typed so that the programmer has access to all of that information readily, directly from the code, and ones in which things are untyped, or rather the typing is hidden and it's only available to the interpreter or compiler. And it can be hard for the programmer to reason about what they're computing. You have an object called data. You're like, what is data? Is it a data frame? Is it a list? Something else? It really matters for how you write code with it. And same thing in math, it matters what kind of an object you're dealing with when you want to perform operations with it. So there's only one correct answer, which is a list of vectors. You take the span of a list of vectors. Occasionally we'll talk about the span of a vector, but that's really just shorthand for the span of the list containing that single vector. Now, a couple of people said something along the lines of a set of vectors, and that's very close. It's better to talk about lists than sets, because sets, as we discussed, don't allow repetition. And you want to be able to say something like, these three vectors, where the first two happen to be equal to each other, are linearly dependent. And if you insist on using a set of vectors instead of a list of vectors, you can't do that, because a set can't contain two copies of the same thing. So that's why we talk about lists. Also, lists are ordered, and sometimes helpful to think about order when we're talking about linear dependence and span. The order doesn't affect whether a particular set is linearly independent or whether it spans a particular vector space, but it can still be useful for setting up certain proofs or thinking about, sort of progressively working through the list in some way. Okay, so that's a great thing to have down pat. So you really want to lock this down. Whenever we talk about span, it's always a list of vectors that we're taking the span of. That's the nature of the operation. You can think of span as a function that maps the set of lists of vectors. So the kind of input that it can take is only a list of vectors. And as an output, it gives a vector space, a set spanned by those particular vectors that it was given. Okay, what kind of geometric pictures come to mind when you think about the word span? Okay, great. So this looks good. I will summarize what everyone said so you can see kind of where folks are on this. So you think of like a plane. So if you have two vectors that are not pointing in the same direction or opposite directions, their span would be a plane. Flat spaces, this is a great answer. points, lines, planes, that kind of stuff. There are a few answers here that are not correct in instructive ways. And you can see that several people had them along the same line. So this is a good thing to address. So for one thing, there's the idea of a lattice. So I think people are getting this from the data gymnasia to help you understand the idea of a linear combination. But when we talk about span, we're specifically talking about all real values that you could scale the two vectors by. So if you consider integer combinations, you can get like a grid or a lattice shape, but when we're talking about span, it's specifically all real combinations. So you would get all the points in between as well. So this is sort of close, but it's assuming a different collection of scalars, a different collection of values that we're going to scale these vectors by than we're actually going to do. The other theme that came up is bounded shapes. So cubes or spheres, those shapes are not going to characterize a span of any collection of vectors because they're bounded. So if you consider one point that's in that shape, you could scale that point infinitely, in the same direction, farther away from the origin or in the other direction as far as you want. And you're going to get this infinitely long line through the origin and through any point. So you can't just sort of go a certain distance and stop. You have to go any direction you go in, you have to go infinitely far in that direction. So it's really the right idea is like these flat spaces that go out to infinity. If you think about a plane through the origin in 3D space, that does have the property that whenever you stretch a vector that's in it, you're still in it. Let's chat, Luke. So Luke has this question following up on the question about like, okay, cubes aren't smooth, but spheres are smooth. So maybe that makes a difference. What if we're talking about in spherical coordinates? Do you want to ask your question out loud? I've been talking a long time. When we talk about linear structure, we're specifically only using linear functions. So that's functions of the form constant times variable. That's it. If you think about spherical coordinates, the way that you have to map real numbers to a sphere in three-dimensional space involves trigonometric functions. Those functions are nonlinear. So, the answer to your question is just yes, that's correct. Spherical coordinates are not a linear algebra concept, and it's because they involve nonlinear operations. So the idea is like, I'll pop open my drawing tool. The idea is like, imagine a circle, which is a sphere, but in 2 dimensions. You have a point on this circle. Let's say this one. Let's say this point is on the circle. And if that point is in the span of some vectors, then certainly, let's say the origin is here. Certainly this point is also in the span because we could just like double all of the coefficients that got us to this one, and that would get us to this point. So anytime a point is in your vector space, every point on the line through the origin and that point has to be there as well. So if you have a vector space or a span of some vectors, which includes the unit circle, then in fact it has to be the entire plane because you could draw all these lines through points on the circle and you would get the whole plane. This is the idea you want to have in your head. Like if you have this orange vector and this green vector, you can scale them however you want, and the sum of the two vectors sweeps out. And in this case, I'm just sweeping out kind of a couple lines here, but you can imagine varying the orange one and the green one sort of however you want to get the purple one to go wherever you want and fill out that whole plane. So this is the mental model you want to have when you think about span. Okay, that was a great question, Luke. Thank you. Okay, here's another question. If we want a list of k vectors to actually sweep out a k-dimensional space, then what has to be true of those k vectors? Okay, great. So people are really on point with this one. I'll just share a few of these answers. Yeah, so Manlin, do you want to explain why the vectors have to be linearly independent? Just conceptually. Yeah, that's a great answer. That's exactly what's going on here. If you have one vector, you can sweep out a line. If you have two vectors, you can sweep out a plane and so on. But if at any point you choose a vector which is already in the span of the ones that you have, you've wasted that one. You're not using that to reach in a new direction. You might as well not have used it. And now you have not enough vectors remaining to reach up to k dimensions. So conceptually, that's what's going on. It's not a mathematical proof, but that's the idea you want to carry in your head. And Yuetian had a good point here that I didn't really think of. It's implied by the fact that the k vectors have to be linearly independent, but it's worth noting they do have to have at least k components. So if they're living in a d-dimensional vector space where d is smaller than k, then they can't possibly fill up that space. Or rather, they will fill up that space, and then the later ones beyond the first d vectors can't possibly be linearly independent. So yeah, we need to have enough. We need to be working in a Euclidean space that has enough room to even have a k-dimensional subspace in it, and then we need all k of them to be put to good use. Okay, so yeah, so the point is the vectors have to be linearly independent. So roughly speaking, this means that every vector represents a fresh direction. And more technically, it means that every vector is not in the span of the other vectors in that list. And that's also equivalent, and this is a question on the homework, so you've probably already seen it, but that's equivalent to saying that the second is not in the span of the first, the third is not in the span of the first two, and so on to the end of the list. So here's where it's helpful too to have a list which has some order structure to it, instead of just talking about a set where you can't really say what's the first element of a set, what's the second element of a set, because it has no order. Here we're taking advantage of that to draw this equivalence between this sort of simpler to think about notion of linear independence, where you only have to check that each new vector is not in the span of the previous ones, and the sort of full-fledged definition, which says that no linear combination of all of the vectors is equal to 0 except the one with all 0 weights. Or in other words, no vector in the list is in the span of the others. Okay, so we touched on this already because of discussing Etienne's point, but I'll ask anyway. So what is the maximum number of linearly independent vectors we could have in R50? Okay, so time's up here. Correct answer is 50. Folks are pretty on point with that. Yeah, so we can have at most 50 linearly independent vectors. The idea is after one vector, we have a line, after assuming it's non-zero. After two vectors, we have a plane, assuming the second isn't pointing the direction of the first. After three, we'll have a 3D space, and so on. Once we get to 50, we'll have filled up the entire 50-dimensional space, and it won't be possible to come up with a 51st vector, which is not in the span of the previous 50, because literally anything it could be, we already have covered that as a linear combination of the first 50. Okay, so we've used this term a little bit just to emphasize it, kind of revisit it. So a set of vectors that can be written as a span of some set of vectors is called a vector space. So this includes all of the Euclidean spaces like the number line, the plane, three-dimensional space, and so on, as well as linear subspaces within them, things like lines through the origin, planes through the origin, that kind of stuff. So we've talked about linear independence and span, and we want to pull those ideas together into a single word, which is basis. So if you have a list of vectors which is linearly independent and it spans a particular vector space, then we call that a basis, specifically a basis of the vector space that's being spanned. And in a linear algebra course, you will go through the work of showing that any linearly independent spanning list has the same number of vectors. So if we fix the vector space and we say, okay, what are two different ways we can come up with a list of vectors which is linearly independent and spans this space, that's always the same for any given vector space. And that number is called the dimension of the space. So if it's like a plane, the dimension will be 2. That means that any linearly independent spanning list for that plane will necessarily have 2 vectors in it. You can't have fewer because it wouldn't cover the whole thing. You can't have more because it would be linearly dependent. And I'll just give you kind of a link in a very short description rather than going through this proof, because I'm not sure it's worth class time, but just to kind of point in that direction. So the geometric intuition here is very suggestive. If you have, as I said, a plane in three-dimensional space, you need exactly 2 vectors to sweep it out. One's not enough, 3 is too many. And you can make that intuition rigorous using linear algebra ideas. So build it up from the fundamental concepts of linear algebra. As I said, we're not going to get into that, but there are some notes here. And there are lots of ways to do this. I really like this one by Sheldon Axler, which I wrote up in these notes when I taught a linear algebra course a few years ago. And roughly speaking, the idea is to take two lists. You want to show they have the same length. And basically, you grab one vector from one of the lists and sort of tack it on at the beginning of the other list and kind of work through that list using the definition of linear dependence. And sort of over time through a process, replace one list with the other in a way that the length of the list is always preserved. And that way you can say, okay, they had to have the same length to begin with. So it's a very nice proof. It's resting directly on top of core linear dependence and span ideas. It doesn't tap into any sort of matrix tricks where you have to do like row echelon form and talk about pivot entries in a matrix and stuff like that. That's what you normally do in a linear algebra class. I think this proof sits in one's head much more nicely and sort of feels less hackish, but it's a matter of taste. Also, I think ultimately you should feel free to rely on the intuition here. It is correct, and the proof adds some maybe internal satisfaction, but it might not be necessarily super useful. Okay, what can we say about the relationship between the dimension of a vector space and the length of any list which spans that vector space? So not necessarily a linearly independent spanning list, but just a spanning list. What can we say about those two numbers? Okay, Radhika, do you want to talk about your answer? Lots of folks had good answers here. Nice job. That's great. Yeah, that's exactly right. So there's some, in addition to the basic fact that any linearly independent spanning list has to have the same number of vectors, namely the dimension of the space, there's also an inequality that runs in, we'll see both directions. So a spanning list has to have at least the right number, but it could have more. That's exactly right. Okay, so you probably know what question is coming next. What can we say about the relationship between the dimension of V and the length of any linearly independent list of vectors in that vector space? Yeah, so this is the first class of answers which said the linearly independent list must be equal in length to the dimension of V. And then a bunch of people also said that it can't be larger than the dimension, but maybe it could be smaller. We have this inequality here. We've got to decide what's going on between these two because people are really split. And the point is that a linearly independent list does not need to it doesn't need to span anything. That's a separate requirement. So when we talk about linear independence, consider, for example, the plane. So that's a two-dimensional space, of course. We could consider the span of a list which contains only this one green vector. All right, that span is going to be a line that runs like this, and it's going to that vector is definitely linearly independent. The span doesn't cover the whole 2D space, but that's not part of the requirement. We're just asking that the any vectors in our list not be already represented by other ones, and here we meet that requirement. If we move up into 3 dimensions, we could do the same thing with 2 vectors that don't span the whole space, but they are linearly independent of each other. So the equality only comes from making both assumptions. Spanning lists are dimension or longer, linearly independent lists are dimension or shorter, and only if you make both assumptions can you conclude that it has to be exactly equal. Okay, so least swaps with most here. Okay, so what's good about bases? Why do we make the assumption that a list is both linearly independent and spanning? Well, one of the most important reasons is that it allows us to represent any vector in the vector space uniquely as a linear combination of those particular vectors. And the weights in that linear combination are called the coordinates of the vector with respect to the given basis. So we do this often in the plane. We'll have what are called the standard basis vectors, which are the unit vectors pointing due east and due north. And the coordinates of a point are just like how much of the first one do we need to add, and how much of the first one do we need, and how much of the second one do we need, such that when we add those, we get the desired vector. So that's a thing that you can do with standard basis vectors, and it's not a surprising or new thing. It's what you've been doing with Cartesian coordinates your whole life since you first learned Cartesian coordinates, probably as a kid. But we can also do it with other vectors. So for example, this teal vector and this teal vector together, they form the list containing those two vectors forms a basis of R2, which means that we can reach every other point with a linear combination of them. And so I want you to figure out how to reach this orange point. So adjust the weights here so that the sort of transparent orange point or transparent orange vector lines up with this one. So how much of this teal vector do you need and how much of this teal vector do you need in order to reach this one? Right, those weights will be the coordinates of this orange vector. Yeah, so people are coming in with very similar answers here. Yeah, so let's do this together. So I tried to kind of help out a little bit here on this one by making the orange vector perpendicular to one of these vectors, because that means you're going to have to adjust the weight for the other one in such a way that you sort of get on this parallel line, because this one doesn't help you at all in the orange direction. It's just going to compensate for what the other one does. So we try to get it on this parallel line like this, and then we move this one like that, and there it is, negative 1.5, negative 2. So anyway, the point is these, the coordinates of this point are 1, 1 with respect to the standard basis. Well, with respect to the basis consisting of these two teal vectors, it's negative 1.5, negative 2. So it's a different way to coordinatize the space. Okay, so I want to answer one question that came in a little bit ago that I missed when it came in. I just asked me to explain again, under what condition the dimension of a vector space is equal to the linearly independent list of vectors in question. So the point is that a linearly independent list can have length equal to the dimension if it spans the vector space, or it can have length less than the dimension of the vector space if it does not span the vector space. So as you build up a linearly independent list of vectors in the vector space, so just grab a non-zero vector, grab another one that is not in the span of the first one, grab a third one not in the span of the first two, and so on. All of those lists, those intermediate lists of vectors that you'll be building up, they all fail to be as long as the dimension of V until you get to the very last one. So you'll have all these examples of vector space, of vector lists which are shorter than the dimension of V and are still linearly independent. So yeah, it's equivalent here. If you want to talk about the dimension of the vector space being equal to the length of the linearly independent vectors, linearly independent list of vectors, it's equivalent to just say that they span the list. Once you know they're linearly independent and there's the right number of them, they necessarily span the vector space. Okay, so all right, this problem was kind of cooked up to be manageable by messing with some sliders, but obviously this is a pedagogical device. In real life, you don't want to solve systems of equations by trying to set up some sort of geometric object on the screen and then using your fingers and a slider to try to figure it out. You want to do it computationally. You want to be able to sort of bake it into a Python program you can set up to run regularly on a server whenever you need to solve that particular problem. So I want to take a look at that. I'm going to give you, I'll give you a little more time actually, because I think it might take some doing. But I want you to write some Python code that basically translates this picture into some sort of function call that allows you to extract these values, negative 1.5, negative 2, in a way that, is repeatable. If the numbers were different, you just change the input numbers and you get the correct answer for the new problem. So this is trying to bring some reproducibility to what we managed to achieve graphically in this figure. Okay, so let's do this together. The timer ran out, and I can really see where people are going with this. I think folks are mostly on the right track. There are two things I want to say. One is that you really don't ever want to use the input function in scientific computing because people don't want to use your program at the command line. As soon as you use the input function inside your function, then it's no longer a pure function and can't really be used outside of a context where someone's going to be entering data at a command prompt, which is never the case. You want to feed the data in somehow, in some sort of pipeline from a data source. So that's just a kind of style idea. You can hard code the data directly into the program, but you want to write your function in a generic way. So that's one important idea. And another one, which I think applies to more folks, is that you don't want to hard code the solution to the extent possible. If we can use general tools that solve a problem in a more general way, then that's better because it expresses our intent more clearly than if we had to hard code specific numbers in our actual solving function. And it will be easier to change if we decide we want to change which teal vector we're talking about here, move it somehow. We want to be able to make a minor modification to the program. And if there's sort of manual math work that's embedded in the logic of the function, then that we can't do that. We have to do that math work all over again if we want to change this. Whereas if we write this in a generic way, then we won't. We're offloading as much of the work as possible onto libraries which handle these very standard operations in robust, fast ways because they've been fine-tuned over the years. Yeah, okay, so I'm going to do this kind of succinctly. So actually, before giving any code, I'll just kind of point out how this problem rearranges into a matrix problem. So we're just explicitly, what we're trying to do is look for two values, C1 and C2, such that when we add C1 of this first vector and C2 of the second vector, we get the desired orange vector 1, 1. Now, this is kind of a mess to try to work with in a computer because there are variables in it. We don't want to have to represent variables when we don't really need to. If we can keep everything numeric, it's going to be faster and involve less overhead managing libraries that can deal with symbolic objects. We will do some of that using the SymPy package later, but for now, and really whenever you can conveniently, you want to get the variables out of it. So this is a standard way to extract the variables out of an equation like this. We pull them to the side and call a vector C1, C2. So we're consolidating all the unknowns in a single vector, and we collect these coefficients into this matrix here. So according to the definition of the matrix vector product, which says a matrix times a vector is the linear combination of the columns of the matrix with weights given by the entries of the vector, this is telling us exactly that this is a kosher rearrangement or re-expression. And so now we're just trying to solve this linear system, AX equals B. If we call this A, we call this X, and we call this B. We're just trying to solve AX equals B. And that's something we learned how to do last time in NumPy using the least squares function. So I'll actually code this up so you can see from, at a little slower pace. So this is what we did last time from numpy.linealg import least squares. So that's for solving a linear system. And then we can do lstsq. And then what you do is you put the A matrix first, and in NumPy, the way you write, well, it's not really a matrix literal. What you're doing is writing an array literal that NumPy converts to a matrix for you. But in any case, the way you do it is you write just a list of lists of rows. So -2, 2, -2, -2, 1, that's this matrix. That's the first argument of the least squares function. And the second argument is the B value, the thing that we're trying to make it equal to. And we can just run that. And we get our answer, -1.5, -2. And all that looks good. Right, so we get -1.5, -2, and that's consistent with what we found when we used the mathlet. Okay, so really, in some sense, all of that was to say that a choice of basis for a d-dimensional vector space allows us to parameterize that vector space. In other words, to associate with each vector a collection of d real numbers. So in the plane, that's maybe not that inspiring because we could already do that. Just use the coordinates of the point with respect to the standard basis vectors. Just like how far left and right from the y-axis, how far up and down from the x-axis. That's what we're used to. We're just doing it a different way here. So maybe that's not that cool, but it works in other spaces too. So if you had a two-dimensional vector space in R7, you could come up with two vectors that span that space and then describe every vector in that space in terms of how many of each of those vectors you need to combine to get it. So it allows you to describe the space using a pair of real numbers instead of, in that example I gave, you'd have to give 7 numbers to specify a vector sitting in R7. And yes, maybe it happens to be in this two-dimensional vector space, but it's not at all clear. And you have to sort of orchestrate how the 7 numbers move in conjunction if you want to stay on that two-dimensional plane. All that's very complicated. But if you choose a basis for the space and just say, okay, let's talk about the 2 weights we're going to use to combine these 2 vectors, things get much simpler. So I'll show you what this looks like again in the plane, since that's by far where our best drawing tools are. I want to ask, what are the coordinates of this orange point down here with respect to the basis consisting of this green and this purple vector? And you don't have to do computation to solve this. You can look at the grid and figure out how many greens and how many purples does it take to get that orange point. Okay, so yeah, so let's look at this together. So folks were pretty on point with this. I'll summarize their responses. You can see what everyone said. And yeah, the answer here is two greens and -3 purples. Because if we take 2 green steps, that gets us right here. And then if we take -3 purple steps, then that gets us right here. And that's perfect. Or we could go the other way, -3 purple steps followed by 2 green steps, and that gets us here. So this grid is really telling us how this coordinate system works. It's really just like, once you know where a point sits in this grid, then you know what its coordinates are with respect to this basis, just like with a standard basis. If we, moved it like this, so it's like a standard basis, and then, you see where something is by just seeing where it is within the grid, 2.5 over 2 down. It really works the same way if you have a differently shaped grid. This point would be 1 green and -2 purples, or this one would be 3 greens and 2 purples. Okay, so let's wrap up with a question to kind of tie this into some other ideas. Let's think about a data frame. So, imagine that you're a clinician and you're looking at some data. You have some rows corresponding to patients, and you have some columns corresponding to some quantitative data for each of those patients. And let's say you also have a response variable you're trying to predict. So you have let's call it an n by k+1 data frame. So you have k numerical feature variables, 1 response variable, that's what you're trying to predict, and you have n total examples, or n rows in your data frame. What vector space might you be interested in here if you're trying to solve this prediction problem? So how does this correspond to vector spaces? Okay, so here's a great answer. So the k feature variables we can think of as column vectors. In your data frame, each column describes the feature for all the patients, that particular feature. And we can start thinking about linear combinations of those columns to try to predict the response variable. So we might want to say, multiply this variable by 3 and this variable by 2 and add the results. And that's going to get you pretty close to the response variable. If that were true, you'd want to know that, because then you could use that linear combination of the feature variables to try to predict the response variable. And really what you'd want to do is try to do the best you could, like figure out what linear combination of the columns, the k feature columns, gets the closest to the output vector. So yeah, so you want to look at the vector space spanned by the columns, the feature columns, which is very likely to be k-dimensional. If there's some reason there's going to be some linear dependence among the columns, then it could be less than k-dimensional, and that's something you'll have to watch out for. But in a general real-world situation where the variables are different from each other, there's almost never going to be a linear dependence relation there. And this vector space is interesting because it's the set of response vector predictions that we can get in a linear way from the variables when we're trying to make a prediction. And so if the response vector happens to be pretty close to this vector space, that's good news, because it means we just need to figure out the right coefficients to get us to that nearby point. And we're effectively predicting the response variable pretty successfully just using a linear function. And that means maybe we don't need to get into more complex modeling, which could run various risks and have costs that we might not want to incur. And that's a good stopping point. Hopefully, that kind of illustrates how it can be interesting from a data science point of view to think about vector spaces and the geometry of vector spaces, even though in a data problem there's not necessarily obvious geometry going on. You can give a geometric interpretation to the data and get something useful out of it. We'll certainly talk about that more later, and in particular we'll revisit this example when we talk about orthogonality, because that's the extra ingredient we need beyond just linear dependence and span to talk about what it means for a particular vector to be close to a vector space and how to come up with the weights that would get us to that, closest point. Yeah, so class is adjourned. I'm curious though, if you want to stick around for a minute or two. I have been, as I'm sure you've noticed, leaning more towards taking a little more time and getting responses to everyone. So it's more interactive in the sense that people are getting actual responses from me to all of their answers, or almost all of their answers in class. Hopefully that's been the experience that you've had. But on the other hand, it's kind of less interactive in the sense that normally you have some sort of stimulation all the time throughout class, and here there's kind of a lag where I take maybe 90 seconds to respond to everyone, where maybe it only took you 45 seconds to answer or something. So I'm curious how you feel about that trade-off. Yeah, that's a great point. The extra time, it creates a little breathing space for people to sort of rest with the ideas a little bit more. And one of the benefits of that is people can ask questions that sort of follow up. Yeah, I value that feedback, Cynthia, and it's incredibly interesting to me how consistent that message is. So here are what people had to say. Okay, people like the pacing slower this way, and they say they like the personal feedback, which is interesting because earlier I asked this question. Earlier in the summer sessions, I asked this question, and it was more the issue of pacing was more all over the place, and I was going faster then, so more people were saying, I find it's a little slow. I guess maybe what happened is that people who found it too slow started just watching the YouTube videos where they can like speed it up at 2x speed or something like that. But yeah, I mean, I obviously want to, whether it's a selection bias or not, I want to address the needs and desires of the people who are actually here. And it seems like this pacing works really well. There is this one concern though, which is definitely a thing that I do. Yeah, I think it's fine as long as it doesn't lead to front loading the material outside of class to compensate. That is definitely a thing that I do. These lectures, if you're only doing the lectures and you're not doing any of the pre-reading, it's hard for me to imagine that it's enough. And that's on purpose. I think if you try to go fast enough to really compensate for people not doing any reading, then it's just way too fast. But yeah, I mean, of course, there's a spectrum, and maybe it's possible at the moment I'm leaning a little too much on the pre-class reading materials. I mean, part of the idea for me is to make the pre-class reading materials so good that it's not like reading a textbook. Like it feels more interactive, and there's more to kind of grab onto there in terms of mental aids and supports that are provided, that the outside of class reading is actually much more constructive than it might otherwise be. Yeah, that's great to hear. I definitely want to make it a good complement. In the past, I have tried to just sort of add voice to it, essentially like cover the same content in the data gymnasia, but in this format, because some people like it more. And I think it's pretty clear that's a mistake. I think it's better to use this time to kind of editorialize more, have some exercises, reemphasize the important ideas, rather than trying to sort of walk through the content again. So I'm glad to hear that you like this. I would really rather cover less material and make sure that you're feeling like you can, more or less stay on top of things than, put the foot a little too hard on the accelerator.